let's spend a little time discussing the Aldol reaction. So if we have a couple of aldehydes, we can get them to react together to make a new bond and a new type of functional group. Typically this occurs in base, and we'll always have some water around. We're going to leave the heat off for a minute. So the first thing we do is to deprotonate the alpha position. Just like that. This is a resonance stabilized enolate. You can draw it both ways if you want to. And now I can use this enolate as a nucleophile to attack the other aldehyde. Basically, I have a big pot of this aldehyde. I add some base, I let it react, and they react together. Two aldehydes react together to make the product. So let's see how. There's my newly formed carbonyl. There's the original alpha carbon. Here's the new bond that I just made, and that new bond is between this carbon, which is this carbon, and the carbonyl carbon, or what used to be the carbonyl carbon, now has an O-, and it has an H attached to it and a methyl. So I got this O-, and the last step here will be proton transfer from water to make the neutral species. And let me try to make that a little more clear. So this is an addition reaction. And indeed, I think you'll recognize that I have the same formula. If I add up all the carbons and hydrogens and oxygens here and add them together, I have the same number. I have not lost anything. There is no byproduct here. So this is sort of base catalyzed. It is very important that you keep track of carbons. If you want to label them, we can go like this: 1, 2, 3, 4, 1, 2, 1, 2. Those are the same carbons there. And you can see that I'm now making a bond between 2 and 3. So 1, 2, 3, 4, 1, 2, 3, 4. Those are the same carbons that we've tracked all through the mechanism. And I encourage you to use that habit in the future, because it's very easy to lose track of a carbon in this type of a mechanism. We can also do a retro-Aldol reaction, and that's where we have a molecule that has it has a beta alcohol, a beta keto alcohol. That's what I'm trying to say. So this is a beta keto alcohol, and it can undergo a retro-Aldol reaction in the presence of base and water. So what we'll do is we will remove this hydrogen first. We're basically going to draw the mechanism I just drew in purple backwards. I just made some water. Now I have this alkoxide, and that can form the carbonyl. It can break the CC bond, forming a new alkoxide. And now you see I've got an enolate plus a ketone, similar to the intermediates I had in the previous reaction. And then when I protonate this enolate with water again, I will end up with a pair of ketones in this case. So this is called a retro-Aldol. Let's label that. And again, let's keep track of carbons. This is a numbering you could do probably before we did the mechanism, but let's just number them anyways so that we can see how they are accounted for. So you can see that I've broken the bond between 3 and 4 with my blue arrow there, and I have now 3 in this case no longer has a bond to a carbon on the right side, so this must be 4. Sorry, this is 4. So you can see that 4 is where the carbonyl was. and 5 and 6 were the methyl groups that really played no role in this. They were just along for the ride. And so that's how we might keep track of carbons in this manner. Again, I encourage you to do a good job keeping track of carbons. So let's look at a few practice problems. Predict the products of these aldol reactions. All right, so again, let's add some numbers here. I have carbon 1, 2, 3, and 4, and I know that carbon 2 is going to be a nucleophile, and it's going to make a new bond with carbon 4 on another one of these aldehydes. So let's draw another aldehyde and give it a different numbering scheme so that we don't get confused. So 5, 6, 7, 8. So I'm going to actually make a new bond between carbons 2 and 8. So I'm going to draw that here. So carbon 8 will form the alcohol. It has the aldehyde hydrogen on it, and it has the isopropyl group. So let me see if I can number these properly. So that looks kind of weird. We can actually draw that a little bit more clearly if we straighten it out. So there's carbon 8 with the alcohol. There is carbon 4 with its aldehyde, and then I need to add carbons 1, 2, and 3, like that. So let's make sure we can recognize these again. I actually think I didn't keep track of my carbons. Let's try this again. All right, so carbon number 4, 2, 8, 6. Those are the important ones. You can see that the new bond was formed between 2 and 8. 2 is the alpha carbon on one of the aldehydes, that's the nucleophile, forms between 8, which is the electrophile on a different aldehyde. We can do the same thing with this second example. We have nucleophilic carbons here. We can form a new bond to another aldehyde. There's my original aldehyde. There's my new bond that's formed. I know that this carbon is what used to be the carbonyl carbon, so I'm going to turn it into the alcohol. I'm also going to give it the aldehyde and its other substituent, the basically benzylic group. And I can stretch this out too if I want to. Let's see what I can do with that. I'm going to abbreviate the phenyl ring there, but you can see in this case I've made this bond. Let's go ahead and number our carbons again so we can keep track of them. And really I think I'm going to redraw this molecule again. So I have 2 of them. One can be the nucleophile, one can be the electrophile. And so I'm just going to go 1, 2, 3, 4. And we'll see that carbon number 1 is my nucleophilic carbon. That's this carbon. Carbon 2 didn't play a role much. Carbon 4 received the nucleophile, and carbon 3 didn't play a role either. And so I can renumber them again, 3, 4, 1, 2. And you can see that I've made a new bond between carbons 1 and 4. So this carbon lost its hydrogen. I drew a mechanism so that I can attack carbon number 4 to make the new bond between 1 and 4. We can also look at this as a way of recognizing that an aldol reaction took place. Here we have a beta alcohol next to our carbonyl, right? If we were going to count alpha beta, the alcohol is on the beta position relative to the carbonyl. That's a good way to recognize that, hey, we used an aldol reaction to make this bond between 1 and 4. So that might be a synthetic tool as a way of working backwards. Let's look at Aldol condensations. So if we take our aldol product that we saw a few minutes ago and we keep it exposed to base and we add some heat, we can actually get it to eliminate. So this hydrogen is still acidic. It's an alpha hydrogen. We can remove that hydrogen. And we can again show some resonance if we wanted to. Resonance helps us understand why we can eliminate, why we can remove that hydrogen using the base. And so we can now kick off OH minus, reforming the carbonyl, forming a new pi bond, and making a product that looks like this. So this is called a condensation product because, let's see, so this step here produced water. So I'm going to draw water as a byproduct down here. That's actually more appropriate of what to show up here because water is produced and OH is regenerated via this step. So we're not actually generating any OH. We're simply reproducing the base that we used in the first step. And so this is why it's called a condensation, because we're making a small molecule. And maybe you're having a problem with me losing OH minus. I hope you are, because that is indeed a poor leaving group. So what's up with that? Why can we do this? This mechanism that I showed right here is called the E1CB, E1 conjugate base. And this is where we do the proton transfer first instead of second, like you were used to seeing with an E1 type mechanism where you form the cation and then do the proton transfer. We can kick off this OH minus because we're under reasonably harsh conditions and we are already in base. So it's not like we're creating new base. There's already base present. We used base in the first step. So to create another base is not really a big deal because we're already in base. Condensation products are high yielding. So that's one check mark in their favor. Sometimes it's hard to avoid forming the condensation product. Sometimes we can't stop at the aldol addition product. It just goes all the way to the condensation product. And that's because this alkene is pretty stable. It's conjugated. So that's sort of the driving force to produce this reaction. So we could look at a question such as this one here. Predict the product. And we're going to have this molecule react with itself. So I'm going to go ahead and draw another molecule. NaOH, heat. What is the outcome? Well, you should recognize this as the setup for an aldol condensation because of the heat. We've got alpha hydrogens right here on the methyl group. We don't have any right here, so we don't have to worry about which side is deprotonated. So basically we want to choose one of these as our nucleophile, one as the electrophile. And I'm going to go ahead and number carbons. Hope you've recognized by now that that ring is simply going to be along for the ride. We don't really need to worry about it, so I'm not going to number it. I'm just going to number 6 different carbons here. And so we can identify carbon 3 as our nucleophile and carbon 5 as the electrophile. You could do vice versa if you want to. It really doesn't matter. So I'm going to redraw then my first molecule. Now carbon 3 is the nucleophile. It's going to attack carbon 5. Carbon 5 is going to form an OH. It's going to be attached to the methyl, carbon 6. It's also going to be attached to the carbon 4, which is part of the 5-membered ring. All right, so let's number those again. 5 is the one that was bearing the OH, 6 is the methyl, 4 is part of the ring. And then, of course, this is in heat, so we expect to do a condensation. We're going to remove the H at carbon 3, we're going to move the OH, and all I have to do is just draw the resulting alkene that's formed, keeping all the other carbons present. So let's number this again so that you can follow along with me. There are my numbers. They stayed the same throughout this reaction. And you can see now we predicted at the beginning that we'd form a new bond between 3 and 5. And you can see that we lost 2 of the H's on carbon 3. So these 2 H's are gone. So is this O. And so the byproduct is water. Again, it's a condensation reaction.